Chapter 16.4 Forecasting with Seasonality. Early in the chapter, you learn that a time series could consist of one or more of the following type of component: trend, seasonal, cyclical, and random. We've already discussed using the trend component to generate a forecast. In this section, we'll investigate the benefit of including a seasonal component in our forecasting method. Recall that a seasonal component is present in a time series if a consistent pattern associated with a calendar can be observed in the data. We'll explore these methods using our new car sales data, which are again shown graphically in figure 16.12. It appears there might be a consistent seasonal pattern in the car sales data. Notice that sales spike upward in the even-numbered quarter, or the second and the fourth quarter of each year. Perhaps we can use this pattern to our advantage when forecasting future sales. Multiplicative decomposition of a time series. The first technique that we'll examine attempts to separate the trend and seasonal components of a time series using a method known as decomposition. In this section, we'll decompose the time series we are studying using the multiplicative decomposition model described in equation 16.11, where yt is the time series value at period t, tt is the trend component at period t, st is the seasonal component at period t, rt is the random component at period t. Notice that I did not include the cyclical component in equation 16.11. This is because cyclical patterns, which vary with the economy, often require a long time frame to identify than our 3-year car sales data provide. To use the multiplicative decomposition technique for a forecast, you need to take the following 4 steps. 1. Identify the seasonal components. 2. Deseasonalize the original data using the seasonal components. 3. Identify the trend component with the deseasonalized data. 4. Use the trend and seasonal components to forecast future period. Identify the seasonal components. Earlier in the chapter, you learned that a seasonal component is a consistent pattern in the data that can be associated with a calendar. The number of seasonal components equal the number of seasons within a calendar year. With our new car sales data, we have 4 quarters for each year, which result in 4 seasonal components that we need to identify. For example, the first quarter consists of months January through March. The second quarter consists of months April to June, and so on. We start this process by calculating a 4-period moving average because of our 4 seasons, centered on the original time series data, as table 16.14 shows. This procedure is not to be confused with the simple moving average technique we used earlier in the chapter. We began by averaging period 1 to 4 and associating this average with the center period, which is period 2.5. The average of 1, 2, 3, and 4 is 2.5. Our result as follows. Period 2.5 average is equal to 120.50. These figures are in red text and highlighted in yellow in table 16.14. As shown in this table, the value 120.5 is halfway between period 2 and 3. Next, we move down one period to calculate the average sales for period 3.5 as follows. Period 3.5 average is equal to 126.25. We continue this averaging process for the rest of the time series, stopping at the average for period 10.5 as shown in green text and highlighted in yellow in table 16.14. Because we have an even number of seasons each year or 4, the moving average are assigned to half period, period 2.5, 3.5, and so forth. This happened because the average of the number 1, 2, 3, and 4 is 2.5. As a result, we need an additional step to center each of these averages on whole period, 3, 4, and so on. As table 16.15 shows. These values are known as centered moving average or CMA. We began by finding the centered moving average for period 3. CMA3 by averaging the result from period 2.5 and 3.5 as follows. CMA3 is equal to 123.375. These figures are in red text and highlighted in yellow in table 16.15. We next find the centered moving average for period 4, CMA4, as follows. CMA4 is equal to 129. The final centered moving average is assigned to period 10 and is shown in green text and highlighted in yellow in table 16.15. If our time series contain an odd number of seasons, say 3, the step shown in table 16.15 would not have been necessary. This is because the moving average in table 16.14 would have already been centered on whole period. For instance, the result obtained by averaging period 1, 2, and 3 would be centered on period 2. The purpose of calculating a 4-period centered moving average in table 16.15 is to remove the seasonal component, or ST, from the time series. This occurs due to the fact that our average includes all 4 seasons. By averaging, we have also removed the random component RT because we expect the random fluctuation to average out over time. Now that we have eliminated the impact of seasonality and randomness, the centered moving average value in table 16.15 represent the remaining time series component, trend, or TT. We can express this relationship as the following. CMA T equal to TT. Recall from equation 16.11 that our original time series can be described as follows. YT equal to TT time ST time RT. With a little algebra, we have what is known as the ratio to moving average, or RMA, which is shown in equation 16.12. The ratio to moving average represents the seasonal and random components in the original time series. The first ratio to moving average we can calculate is for period 3, because that is the first centered moving average available from table 16.15. Using equation 16.12, we have the following. RMA3 equal to 0.8754. These values are shown in red text and highlighted in yellow in table 16.16. We continue this calculation down the time series using RM10 as follows. RM10 is equal to 1.0766. Notice in table 16.16 that we have two ratio to moving averages for each season. For example, the two ratio to moving averages for the first quarter are 0.8955, which occur in 2012 or period 5, and 0.8825, which occur in 2013 or period 9. We also know that these values represent the seasonal and random components of the time series. As follows, RMAT equal to ST times RT. To isolate the seasonal component ST, in the preceding expression, we first need to identify a seasonal factor, SFQ, or the subscript Q refers to the quarter number. For each quarter, by averaging the two ratio to moving averages that are associated with each season, as shown in table 16.17. By averaging the two periods, we cancel out the random component RT in equation 16.12. The following equation shows how the seasonal factors for quarter 1, or SF1, is calculated by averaging the ratio to moving averages for period 5 and 9 in table 16.17. SF1 is equal to RMA5 plus RMA9 divided by 2 equal to 0.8890. We repeat this calculation for the remaining season to obtain the following seasonal factors for quarter 1, 2, 3, and 4. SF1 is equal to 0.8890 from period 5 and 9. SF2, 1.1320 from period 6 and 10. SF3, 0.8865 from period 3 and 7. SF4, 1.0624 from period 4 and 8. Total 3.9699. Notice that the sum of the seasonal factors is 3.96699. We need one final adjustment so that our seasonal factors add up to 4, which is the number of seasons in our time series. This process is called normalizing the seasonal factors. It is performed as follows to calculate the normalized season factors NSFQ for quarters 1, 2, 3, and 4. What do these normalized seasonal factors tell us? It appears that in quarter 2, the dealership typically experience a higher volume of car sales than in any other quarters during the year. In fact, we can say that quarter 2 has about 14% more sales than an average quarter during the year. Quarter 1 and 3 generate lower than average sales when compared with the other quarters. This pattern is consistent with what we observed in figure 16.12, which shows that in even number quarter sales spike. We are now ready to assign our normalized seasonal factors to the seasonal component ST for each period of our time series in table 16.18. Deseasonalize the time series. Our next step in the decomposition process is to deseasonalize the original time series. We do this by removing the seasonality from the car sales data using the seasonal components we just computed. Recall from equation 16.11 that our original time series can be described as the following: YT equal to TT times ST times RT. With a little algebra, we can calculate the deseasonalized sales with equation 16.13. For example, the deseasonalized sales for period 1 would be as follows: Y1 divided by S1 equal to 97 divided by 0.8958 equal to 108.3 cars. In other words, if we remove the effect that the quarter 1 season has on car sales, we would expect to sell 108 cars that period. We continue with this calculation for the remaining period to deseasonalize them. The results are shown in table 16.19. Figure 16.13 shows the effect of deseasonalizing the data. The blue line represents the original time series with seasonality, whereas the red line represents the deseasonalized time series. As you can see, most of the seasonal spike in the original data have been removed with the deseasonalized data. Our next goal is to identify the linear trend line through the deseasonalized data using a simple regression. Identify the trend component with the deseasonalized data. Figure 16.14 shows the deseasonalized data, or red line, along with the trend line that best fit this data, or green line. The regression equation that describes the green line will act as our trend component for the decompositioning forecasting method. To generate our regression equation for this trend line, we can use either Excel data analysis function or the simple regression function in PHStat. The following step will demonstrate how PHStat is used for this procedure. Excel for Mac user can find instruction for this procedure in the textbook website. Step 1. Open the Excel file deseasonalized car sales.xlxx or enter the data shown in figure 16.15a. 2. Go to Advanced, select Stat and select Regression, then select Simple Linear Regression as shown in figure 16.9a. 3. Fill in the data section of the Simple Linear Regression dialog box as shown in figure 16.15a. Click OK. Figure 16.15b shows our trend equation in the decisionalized worksheet labeled SLR. The regression coefficients are circled in red. Based on this result, our trend component for the decisionalized car sales data is described with the following linear equation. TT equal to 116.8545 plus 2.5224T. Notice that the p-value for the regression coefficient in figure 16.15b is equal to 0.008 in cell E11, indicating that the period variable is statistically significant. Normally, this would be an appropriate time to test for the presence of autocorrelation using the Durbin-Watson statistic. However, because we have less than 15 data points in this example, the test cannot be performed. Generate forecast with the trend and seasonal component. To generate sales forecast or FT for the upcoming quarter or period 13 using the multiplicative decomposition method, we use equation 16.14. Let's start by determining the trend component, TT, for period 13. LT equal to 132 as follows. TT equal to 116.8545 plus 2.5224T. We replace T with 13 and then we will get T13 equal to 149.65. To find our seasonal component, we need to refer to table 16.18 because period 13 is the first quarter in 2014. S1 equal to 0.8958 using equation 16.14. Our sales forecast for the next quarter is calculated as follows. FT equal to T13 times S13 equal to 149.65 times 0.8958 equal to 134.1 or approximately equal to 134 cars. Because sales are typically lower for quarter 1 as compared with other quarters, the seasonal component reduces our forecast from 149 to 134 cars. With the multiplicative decomposition method, we can also forecast additional quarters into the future. For example, table 16.20 shows how I can generate forecasts for the remaining 3 quarters of 2014 or period 14, 15, and 16. As we discussed earlier in the chapter, be aware that the farther out into the future we project our trend and seasonality component, the less reliable our forecast value will be. Forecasting error tend to increase as the time horizon of the forecast increases. Your boss has to be impressed with your analysis. Look like somebody might be getting pay raise. I told you taking statistics was a great idea. Because multiplicative decomposition require several steps, I've summarized them for you. First, identify the seasonal component by calculating the centered moving average. 2. Deseasonalize the original data by dividing the original time series with the seasonal components. 3. Identify the trend component by performing a simple regression using the deseasonalized data. 4. Use the trend and seasonal component to forecast future period. Investigate the accuracy of the forecast. How accurate is the car sales forecast using multiplicative decomposition compared with the method discussed previously in the chapter? We need to calculate the MAD. First, I will calculate the forecasting error for the first period. The trend component TT for period 1 is follows. TT equal to 116.8545 plus 2.5224T and replace T with 1 equal to 119.4. According to table 16.18, the seasonal component for the first quarter of 2010 is 1.8958. Using equation 16.14, our sales forecast for period 1 is calculated as follows. FT equal to T1 times S1 equal to 119.4 times 0.8958 equal to 107. Our forecasting error is defined as the actual sales value or YT minus the forecasted sales value or FT. For period 1, our forecasting error is calculated as follows. YT minus FT equal to 97 minus 107 equal to minus 10. For the upcoming MAD calculation, we take the absolute value of this forecasting error as well as the remaining errors shown in table 16.21. The average forecasting error for multiplicative decomposition with our car sales data using MAD is therefore as follows. MAD equal to summation of absolute value of YT minus FT divided by N is equal to 84.1 divided by 12 equal to 7. Using this method, our average forecasting error is 7 cars per quarter. How does this accuracy stack up when compared with the previous method we have explored in this chapter? Table 16.22 provides a summary of what we've done so far. As you can see in this chart table, multiplicative decomposition provides the best result. This is not surprising considering the fact that our car sales time series exhibit pattern of both trend and seasonality, and that this last forecasting method is the only one in the table that account for both. It's worth noting, however, that one of the more basic methods for period simple moving average also perform very well with this data set. In forecasting, there is no guarantee that a more complicated method will outperform a simple forecasting technique. Representing seasonality with dummy variables. Chapter 15 introduces the concept of dummy variables. Dummy variables allows us to use qualitative variable in the regression model. We can represent seasonality with dummy variables in our regression model as well. Because we have 4 categories of season, first, second, third, and fourth quarters, we need 3 seasonal dummy variables, which are identified in Table 16.23. For example, SD1 is the first of 3 seasonal dummy variables. I've arbitrarily chosen the first quarter as my base season by assigning a 0 value for all 3 dummy variables in Table 16.23. Our new data set now includes the following variables: dependent variable car sales, independent variables, time period, seasonal dummy variable, SD1, SD2, and SD3. Table 16.25 shows the car sales data with dummy variables for this regression model. This data can also be found in the Excel file carsalesdummy.xlsx. Our next step is to use PHStat to perform a multiple regression on our car sales data. If you recall from the previous chapter, we have some choices as to what multiple regression method to use with PHStat. I will use best subset regression, which examine all combination of independent variables as possible candidate for the final regression model. Excel for Mac user can find instruction for this procedure on the textbook website. First, open the Excel file carsalesdummy.xlsx or enter the data shown in figure 16.16a. 2. Go to Add-in, select PHStat, and select regression, select best subset as figure 16.9a shows. 3. Fill in the best subset dialog box. 4. PHStat create several worksheets in the Excel file, one of which is labeled best subsets. Selecting this sheet will display the data shown in figure 16.16b. Dialog box as figure 16.16a shows and click OK. Figure 16.16b shows that the 4 independent variables provides 15 possible combinations to be considered. 2 power to 4 minus 1 is equal to 15. This figure also shows the adjusted R-square and the standard error for each of these regression models. Ideally, we are looking for the subset with the highest adjusted R-square and lower standard error. The model that meets this criterion, X1, X2, X4, is highlighted in yellow. To find the regression result for this model, go to the worksheet labeled 3x2. Because in the list of model in figure 16.16b, we are choosing the second model in the group with 3 independent variables. Figure 16.16c shows this regression result. As you can see in figure 16.16c, our final model contains the time period and 2 of the 3 seasonal dummy variables, SD1 and SD3. This model has an adjusted R-square equal to 77%, and all 3 independent variables have p-value less than 0.05. The regression equation that we can use for forecasting is therefore as follows. Ft equal to 104.1667 plus 2.5t plus 33.1667 SD1 plus 18.1667 SD3. Once again, this would be an appropriate time to test for the presence of autocorrelation using the Durbin-Watson statistic. However, because we have less than 15 data points in this example, this test cannot be performed. We are now ready to put this bad boy to work for us by generating a forecast for the first quarter of 2014, period 13, so t equal to 13. According to table 16.23, the first quarter of any year uses the following seasonal dummy variables: SD1 equal to 0, SD3 equal to 0. Our regression forecast for this quarter is then as follows. F13 equal to 104.1667 plus 2.5 times 13 plus 33.1667 times 0 plus 18.16.7 times 0 equal to 136.7 or approximately equal to 137 cars. We can also forecast car sales for the remaining 3 quarters in 2014 as follows. Second quarters F14 equal to 104.1667 plus 2.51 times 4 plus 330.1667 times 1, 18.1667 times 0 equal to 172 or approximately 172 cars. Third quarter F15 is approximately 142 cars. 4 quarters or F16 equal or approximately equal to 162 cars. We would be negligent not to check the MAD for this forecasting method to see how it compares with our previous model. So let us go it. First, we'll demonstrate how to calculate the forecast for the 4 quarters in 2011, period 1 to 4, and then summarize the remaining calculation. Excel is also an excellent choice for performing these calculations. 2011 forecast, first quarter, or t equal to 12, F1 is equal to 106.7, second quarter, or F2 equal to 142.3, third quarter, or F3 equal to 111.7, fourth quarter, or F4 equal to 132.3. Table 16.25 shows the forecast for the remaining quarters along with the forecasting error for the MAD calculation. The average forecasting error for multiple regression with seasonal dummy variable is therefore as follows. MAD equal to summation of absolute value YT minus FT divided by N equal to 78 divided by 12 equal to 6.5. Table 16.26 compares this result with the previous model in the chapter. It looks like the seasonal dummy variable model gets the trophy, at least for this particular data set. Both the multiplicative recomposition and the regression with seasonal dummy variable should perform fairly well if the overall trend is relatively linear and the seasonal patterns are somewhat consistent from year to year. I would recommend you provide your boss with a sales forecast of 137 cars for the first quarter of 2014 by using the seasonal dummy variable model. Thank you.